We are currently combining large language models with computational iteration. By granting an LLM access to sequencing, conditionals, and loops, we reach the threshold of Turing completeness. The system can now execute any computation a machine can handle. This reaches back to the earliest days of computer science. Pioneers like Marvin Minsky conceptualized artificial agents as entities capable of perceiving their environment, making a decision, and acting on it. But placing an LLM at the center of that loop introduces an immediate paradox. Large language models calculate the next most likely token based on probability. When they imagine details that do not exist, they are performing as designed. Hallucination is the fundamental mechanism of generation. A severe failure mode emerges when probability-driven text generation governs an autonomous iterating code loop. You are asking a system built for prediction to rigidly manage state across multiple cycles. Look at a naive Python while-true loop calling an LLM. As the agent talks to itself, passing its own outputs back in as new inputs, the logic mutates. The token counts crank up, the context drifts, and the agent wanders out of bounds. The composer John Cage popularized the philosophy that nothing is a mistake, there is only make. That is a brilliant framework for generating art. However, production-grade software engineering requires a different discipline. An LLM cannot logically govern its own probabilistic generation. To prevent iterative drift, engineers must construct deterministic, neurosymbolic guardrails around the model. We have to trap the probability inside a cage of hard logic. Bounding the LLM interface begins with strict type contracts. Technologies like pydantic allow us to specify the exact shape and parameter type we expect an agent to return. A raw block of conversational prose is effectively useless for system control flow. You cannot reliably parse an essay for execution parameters. Type checking forces the agent to commit its reasoning to a verifiable format before a single line of execution can occur. If the variable is not an integer, the loop rejects the action. This leads to the completion bell. An agent can never report its own success using generated text. A clean text summary that the agent did not actually verify is a primary failure mode we have to catch. There is zero value in an LLM saying, "I fixed the issue." We measure success by a hard environmental readback, like a live git status porcelain hash that physically proves the directory is clean. System state must always be derived live from the environment. It can never be assumed from the agent's internal memory or its conversational context window. Forcing an agent to use strictly typed environmental readbacks completely strips it of the ability to confabulate state. If the output does not match the physical machine state, the action fails. This creates the first hard wall of trust. The next layer of defense relies on defining the categories of being. Aristotle introduced this concept to structure human knowledge, separating entities by their properties and relationships. Modern software ontologies apply that same logic. They operate as formal specifications of shared conceptualizations within a specific domain. They define exactly what objects exist and how they are permitted to interact. Relational databases stick data into rigid tables, which breaks easily under iteration. Graph architectures are flexible. They map entities and relationships, but they can enforce strict logical properties across those connections. This diagram maps the neurosymbolic flow. A probabilistic LLM attempts to make a connection. Before that action reaches the world, it hits the ontology layer, validating the model's guess against deterministic graph constraints. Take an OWL functional property, which dictates that an entity can only have one value for a specific trait. If the LLM tries to assign two distinct fathers to a single entity, the ontology repels the request and forces a retry along a valid path. Production ontologies do not require massive, top-down academic models to work. They can accrete bottom-up, directly from the codebase's own tactical axioms, mapping only the constraints the system actually needs. These graph constraints act as an impassable deterministic filter. They sever probabilistically generated logic errors, ensuring impossible states never execute in the real world. Even with strict typing and ontologies, a pervasive failure mode remains in standard agent designs, relying on self-critique loops, where an LLM is asked to verify its own work. This bounding volume represents the Bayesian envelope. It defines the absolute limits of an LLM's internal context window. The bouncing data point is the agent reasoning over its own output. An LLM evaluating its own synthesis is mathematically redundant. It approaches the limit of what the context implies, but the boundaries of the envelope never expand. No new information is added. Internal boundaries can only re-infer existing data. They collapse context into new artifacts, but they do not transmit new truths. To actually move the envelope, the system must cross a boundary into the external world. It must hit an exogenous signal, running a test, reading an unloaded file, or observing an external fact. Executing a grep command on a live external codebase breaches that barrier. It pulls in raw data the agent could not predict, injecting actual evidence into the context window. An agent without an external world-crossing node is trapped in its own prior assumptions. It is mathematically guaranteed to launder its own confabulations. This chart details the leap-null-falsify pipeline, a 3-node architecture built to systematically destroy confabulation laundry. It starts at the leap node. Operating at a high temperature, it samples off the dominant path to generate a creative claim. It produces a candidate idea, never a final conclusion. That claim moves to the null former node. This is a cold, low-temperature environment. It converts the candidate claim into a sharp, falsifiable null hypothesis. The null is handed to the falsifier node. This is the world-crossing execution node. It takes the null hypothesis and actively attempts to kill it by hitting external evidence outside the model's memory. The asymmetry here is critical. Handing an agent a hypothesis to confirm invites motivated retrieval. Handing an agent a null hypothesis invites rigorous, destructive attack. Structurally separating idea generation, negation, and falsification creates a pipeline where the LLM is physically blocked from confirming its own imagined outputs. World-crossing tests and geometric ablations are computationally expensive. Running them on every single token variation will quickly drain a budget. This funnel illustrates the cascade as router. We route tasks through cheap deterministic gates first. We only spend compute on expensive ablation geometry if the cheap filters fail to resolve the issue. When complex tasks do reach the end of the leap-null-falsify pipeline, the result is rarely a clean binary kill or survive. The most common result for memory and estimate grade claims is a coefficient correction. Often, the LLM generates an idea with a kernel that is directionally correct, but it hallucinates a mathematically wrong magnitude. It assumes a localized error is a system-wide crash. The pipeline distills probabilistic ideas into precise mathematical corrections. It extracts the usable signal from the hallucination without overspending on compute. Zoom out to view the entire neurosymbolic architecture. We have a chaotic, glowing LLM core, tightly locked inside layers of pydantic types, graph ontologies, and the leap-null-falsify pipeline. A single probabilistic idea originates in the core. It navigates the deterministic guardrails, satisfies the type constraints, respects the graph relationships, survives falsification, and safely reaches execution. Reliable agents emerge from the synthesis of neural generation and symbolic constraints. Architecture serves as a system-level requirement that prompting alone cannot satisfy. The industry obsession with prompt engineering falls short. Modifying conversational tone does not prevent autonomous drift inside a Turing-complete loop. The modern role of the AI architect is building physical structural boundaries, not tweaking model behavior. You must define strict bottom-up ontologies. You must mandate falsifiable, world-crossing execution loops that prioritize external evidence over internal logic. The architecture makes it impossible for the system to act on unverified hallucinations. That structural certainty is the basis for trust.